Okay, so today we're going to look at an algorithm called the Levenshtein distance algorithm. Alright? It's a really cool algorithm. I consider this to be a very, very sort of handy thing to have in your back pocket. You can use it to solve all kinds of interesting and cool problems. For example, it's used in music retrieval systems. It's at the core of TunePal, which I'll give you a little demonstration of how it's used in TunePal to do melodic similarity, to test to see if one melody is similar to another melody. It's also how every single spell checker works. It uses a variation on this algorithm, and it's used in things like gene sequencing matching and stuff like that. Alright, so it's got loads of different applications, basically for testing to see are things similar to other things. So, okay, to think about this algorithm, it makes use of a matrix. Alright, to think about this algorithm, let's consider these words here. Fred, X or ED, B or EAD. Let's try F or X, E, D, X. Okay, so I got 4 words there, right? So the question we want to try and answer is, like, let's say we take Fred up there as being our root word. Okay? Is Fred similar to any of those other words? Is it similar to the second word?
Yes.
Okay. Is it similar to the next word? E or EAD, F or ED. It's not as much similar, but it's kind of similar. What about the last word? A little bit. Same sequence of letters, yeah, but what have we got in the last one? We have some more letters, right? So we want to try and come up with a way of saying how similar one word is to another word, right? And one way of considering how similar 2 words together is to consider how many edits you need to make to one word to make it into another word. An edit being either an insertion, replacement, so substituting one character for another character, or deleting a character. I mean, we could consider this word as well, maybe. Fred and red. So, if we consider that the cost of doing an insertion, a substitution, or a deletion is always 1, right? Let's consider that it's the same cost for doing any one of those operations. What would you say is the distance between the first word and the second word?
2.
Okay, so delete is also 1. So yeah, definitely. There's 2 possible ways that we could make this into this. We could, number 1, delete the X and insert an F. Alright, and that would have a cost of 2, wouldn't it? Alternatively, we could just substitute an F for the X, and that would have a cost of 1. So yeah, you're right, there's actually multiple costs, but what we're kind of looking for is the minimum cost, because in actual fact there's an infinite number of costs that you could go from here to here. Because you go insert, update, delete, whatever, number of combinations. We'll try and find the minimum cost, right? What about the minimum cost of making Fred into bread? What would you have to do?
Replace the people and then take out the A.
Okay, so number 1 thing we could do is replace this with an F. So we have a cost of 1 for that, and then we delete this one, and then we make that into that, and so we've got a cost of 2 to calculate that one, okay? What about this one here? 6 deletions. So delete, and we get a cost of 6. So now we're getting an estimate. The cost of that one is 1, the cost of this one is 2, the cost of this one is going to be 6, and the cost of this one, 1, because we're just doing 1 insertion. We put an extra character at the end. Do you think you could write a C# program to calculate that? What would it look like? Lots of string operations. How would it work? Would you check each string against each character? How would you know, for example, in this situation here, that you want to do a substitution and not an insertion and deletion? How would you know?
Make sure that they're the same length.
Okay.
Same set of characters.
Yeah, but what we're saying that this is X or ED. Okay, so we reckon we could just do 1 character there. But what if it was F, X, or ED? So we could do a deletion there. Just delete that. Or we could do 2 deletions and 1 replacement. There's loads of different possibilities to go from one string to another string. Or, you know, if we had... X, F, or E, D, then we just have one deletion again. How would you know whether to delete or update or insert? I think it would end up being very difficult. Loads and loads of if statements, and you'd end up putting in loads of little edge conditions, you know. Like, for example, if you were comparing Fred with X, 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 F, X, or ED. Now you'd have to kind of first of all say, well, look at the first character here and search all the way along to find the first character. But what if the character there was P? So then you wouldn't be looking at the first character, you'd be looking at the second character. Can you see how this could get exponentially very complicated very quickly? Yeah? Can you see that? It could get really messy. Alright, so I'm going to show you a better way to calculate the minimum edit distance. Alright? And it makes use of this algorithm which was discovered by a Russian mathematician called Levinstein back in the 60s. I can't remember what the original application for it was, but it's used all over the place now. It's called a dynamic programming algorithm, and it makes use of a matrix to solve this. And it's actually very simple. You guys are going to code it up in the lab this week. It's a very simple algorithm. And here's the simple algorithm. Let's say we wanted to compare the words F or ED with B or EAD. And what did we say the distance between these two was? Well, we have to do a substitution there and a deletion there. So the cost of this to this is going to be 2, right? So we need to write some method which is going to calculate the cost of going from this to this. And this is how it works. What you do is you create a matrix, and the size of the matrix, it doesn't matter which one is the rows and which one is the columns, by the way, they're interchangeable. But you need to take the first word, the length of the first word plus 1, and the length of the second word plus 1, and that's the number of rows and that's the number of columns. Is that clear? So, you know, we've got 4 here, so we're going to have maybe 5 columns, and then we have 5 here, so we end up with 6 rows. So let's do that, right? So that's F or ED. By the way, most importantly, when I'm doing this, we'll do this manually, because you can do these, and I always ask a question every year in the exam to do one of these tables. You don't actually put these letters into the matrix, okay? This is just for doing the operations. So then we look at F or ED, and the very first row of the matrix you set up as follows. So we have one extra one, but you put it at the start. So you put 0 as being the 0th one, and then you do 1, 2, 3, 4, like that. And that's the first row that you set up with the matrix. So then you do the same thing with the columns, and we have B or EAD, B or EAD, like that. And you do the same thing. You put 1, 2, 3, 4, 5, like that. And that's how you set up the matrix. Alright, so number 1, creating a matrix, one bigger than the length of, one bigger number of rows, one bigger number of columns, and you fill out the first row with 0, 1, 2, 3, 4 up as far as the number of characters, and then the first column you set up in it like this as well. Alright, so that's the second step. Now what you do is you proceed comparing each element from the string, character by character, and you apply the following rules. Okay? If the character will say at position, this is going to be column -1. Let's call this string A, and let's call this string. You know what? They have proper names. They're called needle and haystack when you see them written out. But we'll just call them A and B, okay? So, what you do is you check to see if A at position column -1 is equals to B at position row -1. Yeah? Because I'm doing this cell here. Yeah, but this cell here, you know, to get this character here, this is column number 1, but I actually need the string at position 0, don't I? You follow? So I compare the two of them. If they are equal, I put the value from the diagonal down here. Alright? So then the cell at position row and column is going to be equal to the cell at position row -1 and column -1. Okay? Now, okay, so you compare F and B, are they the same? In this situation, they're not the same, but if they were the same, you would just take the value from here and bring it down to here. Is that alright so far? So, that's actually saying that the cost of bringing, well, here's a way of looking at this, right? If you look at this cell here, this is like the empty string, and this cell here corresponds to the empty string. So this is like saying, how much does it cost to take the empty string and make it into the empty string? And the cost for that would be 0, wouldn't it? Taking the empty string, making it into the empty string would have no edits required. And if you look at this, to take the empty string and to make it into B, you would have a cost of 1, because you have to do 1 insertion. You understand? To take the empty string and to make it into B OR would have a cost of 2. So these are simple ones because we're just doing insertions. And the same way you can read it across the top. So to take the empty string and to make it into F, cost of 1. To take the empty string and make it into F OR would have a cost of 2. Do you follow? So what this is saying here is to take F and make it into B. It's the same as the cost of the empty string into the empty string plus the cost of F into B, which is, well, hang on, let's say if these were the same, right? If these were the same, right, then what we would be doing is taking down the value from here. So this is like saying, the cost of making F into F is like the cost of whatever comes before F into whatever comes before F here, plus the cost of making this into this, which is 0. So that's why you take the diagonal down. Is that okay? So we take the diagonal down here, right, and we put this back into B. So the diagonal in that case is 0. Okay, if they're not the same, else we take the minimum of these three and we add 1 to it, 1 being the cost. So we take the minimum of the cell at position row minus 1 and column, the cell at position row and column minus 1, and the cell at row minus 1, comma, col minus 1. So we take the minimum of those three and we add 1 to it. And that's the value that we put in. That's the rules, that's the algorithm, nothing more than that. And you proceed to do that for every cell. So I'll do it, right? So we look at B and F, are they the same? No. So we take the minimum of this one, and this one, which is going to be 0, and we add 1 to it, and so we put 1 in there. Then we look at B and B and OR. These are different, so we take the minimum of these three, 1, 1, and 2. Minimum of those is 1, and we add 1 to it, so we put 2 in there. Then we look at E and B. Again, they're different, so we put 3 in there. Then we do D and B, looking at the minimum of those, and we put 4 in there. Is that clear? Is everyone following this so far? Yep. Okay, let's do the second row. Then we look at OR and F. Are these the same? No. Minimum of these three plus 1 is 2. OR and OR, these are the same. So we take this value down and we bring it down to here. And this is interesting, right? Because if you look at F OR and B OR, the cost is 1, because you have to do 1 substitution. So then we look at E and OR, they're different, so we take the 1 and that becomes a 2. Then we look at D and OR and look at the 3 of these, and then this becomes 3. So then E and F. Minimum of those three is 2 plus 1 is 3. And then we look at E and OR. Minimum of those is 1 plus 1 is 2. And then E and D, these are the same, so we bring down the diagonal 1. And again, we have F OR E to B OR E, distance of 1. So then we look at D and D, and that becomes 2. So F OR E D, B OR E, F OR E D to B OR E is a distance of 2, because we've got to drop the 1 and substitute for the B. So then A and F, they're different, so that becomes 4. F and A are different, so that becomes 3. E and A are different, so that becomes 2. And then D and A are different, so that becomes 1, 2, becomes 2. And we'll do the last row then. So then we do this one. D and F are different, so that becomes 5. D and OR are different, so that becomes... Does everyone follow what I'm doing here? This looks like a really great candidate to write a program to do it, doesn't it? Because it's quite tedious and repetitious, right? You can figure out, it's just a simple algorithm. So then we have E and D, these are different, so that becomes the minimum of those plus 1s, which is 3. And then we have D and D, those are the same. So we bring down the value from there and that becomes 2. Now the minimum edit distance, and in fact the path is basically you go back up here through the diagonals, picking the minimum one, and that will give you, you know, the minimum path. But we're not interested in that. We're only interested in the actual final result. And the final result is in the bottom right hand corner of the matrix. That's the number there that tells us the minimum number of edits you need to make to Fred to make it into bread. And that's called dynamic programming Levenshtein distance algorithm for calculating the minimum number of edits required to make one thing into another string. Now you can do this with strings, you can do it with lists, you can do it with vectors, you can do it with matrices of matrices, doesn't matter. And you can change things like the cost function. You can decide that, you know, the costs are different for insertions, updates, and deletes. And there's a really cool variation on this algorithm called the substring edit distance, which we'll do next, maybe next week, which allows you to say, you know, look at things like, you could look at a big long string like F-R-E-D-R-I-C-K, Frederick, and look for the string Rick, and be able to say that this matches this bit of this string. You know, so you can search for strings. Or even you can look for RCK and say, well, the minimum, the closest match is actually that bit of the string. You know, so we'll search for strings in other strings, even with edits required. It's a really cool algorithm, right? Does everybody understand how to make one of these matrices from scratch? So if I put a couple of words up on the screen, could you write the do the edit distance matrix for some practice? Does everybody understand? Okay, cool. I'll give you a couple of words and do this matrix. And you just take each cell and you make it using these rules here, and you end up with the edit distance matrix. The minimum edit distance is the value down in the bottom right hand corner here. Okay, so here's a couple of words for you, right? Or here's a couple of strings, and I'll deliberately pick some strings that are sort of, let's say we pick a string X, A, B, C, D, Q, P, R, T. Okay? So we pick that string there, and then let's pick the string A, B, Q, P, X. And give me the minimum number of edits required to make this string into this string. Yeah, you can pause it, I guess. Yeah, the pause just usually switches it off, but sure, that's kind of.
I'll edit it so that there's not so much of
Is that the red light, Jack? Yeah. Cool. All right. So I'll just do the first bit of this because it'll take a while to do the whole thing. It doesn't matter which one you pick, okay? But we'll say we'll draw the big matrix, or the big one across the top, the big string. So X, A, B, C, D, Q, P, or T goes that way, and then we put 0 there. X is 1 for marker. 2, 3, 4, 5, 6, 7, 8, 9. Now, when you're doing this thing, okay, this is very important. You don't put this string into the matrix. It's a matrix of integers or floats or whatever. This is just for us when we're drawing it up, right? When you actually write this program, you create the matrix, and this is the 0th row of the matrix. Is everybody clear with that? You don't put the string into the matrix. So then, you put the other thing down this side, so A, B, Q, P, X, and you put 0, 1, 2, 3, 4, 5. So then we compare A with X. They're not the same. So we take the minimum of the 3 of these and we add 1, so 1 goes in there. Is that what everybody's doing? I'll just do the first row. So then A and A are the same, so we take the diagonal and bring it down. And then A and B are different, so we take the minimum and we add 1. Then these are different, so we take the minimum and add 1. These are different, so we take the minimum and add 1. Q and A are different, so we take the minimum and add 1. P and A are different, so we take the minimum And then R and A is different, so the minimum and add 1. And then T and A are different, so the minimum and add 1. And that's the first row. Does everybody understand what we're doing? So that's the first row. Then we'll do the second row. So A and X different, so that becomes 2. A and A are the same, so we take a diagonal and bring it down like that. Is that alright? And then A and B are different, so we take the minimum and add 1, so that becomes 2. Then C and, so what are we looking at? B. C and B are, did I make a mistake there? I did. So we should be looking at B and B, so we take the diagonal and bring it down
And the
there.
one before that should be 2, comparing B to A.
Oh yeah, I'm looking at the wrong row. I should probably draw in lines across here, so I can see which one I'm referring to.
That should be 2, 2, 2.
2, 2, and then that should be the minimum and add 1, which is going to be 2. And then these are the same, so we bring the diagonal down 1. Does everybody get what we're doing here? So then B and C are different, so that becomes 2. B and D are different, so that becomes 3. Then that becomes 4, 5, 6, 7. Yeah. And so on. Does everybody understand how to implement the edit distance algorithm between two strings? So by making that table. Is everybody 100%? Great, so that's going to be your lab this week. Your lab this week is going to be to write a static method on a class which calculates the edit distance between two strings. I want to pass in two strings and I want to get a number back. So if you want to think of step by step how you do that, the first thing you're going to have to do is create a matrix. And we have a matrix that has a constructor that takes the rows and the columns. So the rows is going to be the length of one of the strings plus 1, and the columns is going to be the length of the other string plus 1. Then we need to set the first row and the first column to be 0, 1, 2, 3, 4, 5, and so on, up as far as the width and all the rest of it. And then we need to iterate through the strings character by character, comparing each character, filling out the whole matrix. So probably a nested for loop in there in the middle. And then right at the end, you retrieve the cell in the bottom right-hand corner, and that's the cell number that you return. So would everybody be able to do that in the lab? Yeah? Come on, this is easy stuff. Huh? If this was hard, I would spend a bit more time on it. But this is just a nested for loop, right? Is that okay with everybody? So that's your lab this week. Now, I just wanted to... I know you've probably seen me giving this presentation before, but I'll just show you where this algorithm is at the core of lots of different systems. But just to show you, this is the new version of TunePal. Alright, so I spent a lot of my time over Christmas, and I launched the new version of TunePal, submitted it to Google Play. I suppose it's up on Google Play about 3 weeks now. You know, I've had 1 or 2 minor updates just to fix bugs on particular devices. Submitted new versions to Apple. There's an extra 5,500 tunes in the collections. So, and you know, loads of users, and it supports loads of different new devices and everything. But basically, this algorithm, or a variation on this algorithm called the substring edit distance, very simple variation on this algorithm, is how TunePal is able to so accurately identify all the tunes that people play. So, how does TunePal work? Well, basically, what happens is, when you tap record here, it records 12 seconds of music. Alright? It then uses a thing called digital signal processing to analyze that music and extract the string of musical notes. So the musical notes go from D up as far as G, right? So they're the sequence of musical notes, right? So you get a sequence, a string of musical notes, the notes that the person has played, and they are kind of normalized because if they're in different registers, it puts them all into the same register. You basically get an all uppercase string. TunePal takes that string, sends it up to the server. On the server, there are music scores for 23,000 pieces of music, 23,000 music scores. And every time you try and do a search with TunePal, it generates the edit distance between what you've played and the music scores, all 22,000 of them. And then it sorts them. It sorts them in ascending order of edit distance. So the ones with the smallest edit distances are at the top, and the ones with the biggest edit distances are at the bottom. And then it returns the 20 matches in order of descending edit distance. So that's how TunePal works. So just to show you, you know, how effective this algorithm is, I need a volunteer. Will you come up and hold the thing? Hold the tablet. So this depends on an internet connection, right? I'll just show you. So just hold the tablet there for me if you don't mind. Thank you. And just hit tap to record, and I'll just play a piece of music, right? So it just needs 12 seconds. And it can be from any part of the tune. That's called the Lilies of the Field. And so there you go. Lilies in the Field with 86% confidence, right? So it's gone and done the edit distance for all of those. The interesting thing here is usually you'll find, you know, because there's a lot of duplicates in different tune books, you'll get the same tune from multiple different tune books. So you can tap on Lilies of the Field. It then downloads the music score as an XML file and parses it. Part of the music score is this, which is called the ABC notation for the tune. This is what it's used to generate those strings on the server called search keys, the strings of musical notes on the search keys. They're all generated from this ABC. And you can do things like you can play it back. You know, so it takes the ABC score and converts it to MIDI and plays it back. And you can do lots of things like share it on Facebook, share it on Google+, various other things like that. Yeah, if you like the tune, then you hit plus and it saves it onto your device, saves it on the device in a thing called MyTunes, and then it has this really lovely swipey thing as well. You can also do keyword searches, so you can just type in the name of a tune as well and it will search through them, but obviously that doesn't use edit distance, that just uses an SQL query. So it's just an SQL query, you know, it uses a like as part of the where clause in the SQL query to be able to return, you know, tunes with a particular word in the title of it. So that's how it works. But yeah, before I finish this little demo, I just want to show you this algorithm in action. So actually, can you come up again for another go? Thank you.
Why is it 12 seconds specifically?
I picked it because I did some timings. I want to get the entire, if you like, typically in trad tunes there's an A part and a B part. 12 seconds allows you to get, depending on the tempo that you're playing, at the entire A part of the tune. But also I extended it to 12 seconds. Shazam by default used, at the time I was writing this, Shazam used 10 seconds. So I used that as my kind of, I said I'll use 10 seconds, but then I decided 10 seconds isn't quite enough, 12 seconds is actually better, you're more likely to get a match if you use 12 seconds. But again, just to show you this edit distance, right? So now I'm going to have a higher edit distance because I'm going to make loads of mistakes. And you'll see that it still finds the correct match. And in fact, this algorithm is so unbelievably brilliant at matching trad tunes that it's 93% accurate. Even really noisy pub sessions, lots of foot tapping, you know, doors slamming, the till going, people cheering, everything. So long as it gets even a small segment of the melody, it's almost always able to find the correct match for it, right? So just to show you, maybe I'll do a different tune. I'll do Kiss the Maid Behind the Barrel, right? So, you know. Kiss the Maid Behind the Barrel. So long as it gets enough of it. No, it didn't work. But interestingly, okay, not too many mistakes in it, but you look at number 2 match, number 3 match, number 4 match, Kiss the Maid Behind the Barrel. So it didn't get it as the first match, but it got it as the second, third, and fourth match. So, you know, it's calculated the edit distance between what I've played, or what it has transcribed, and the edit distance for 22,000 tunes from the server, and it's still, even with all those mistakes and everything, able to get it in the top 10 matches. So that's the power of this algorithm. Alright, so it's a fun algorithm, and also it's how spell checkers work. You know, when you type in a word, what your spell checker is doing in the background is it's taking that word, calculating the edit distance between what you've typed and all the words in its dictionary, and saying, hey, you know, this isn't 100% match, but I think you meant these words. And how it figures out those words is it's calculated the edit distance between what you've typed and the words from the dictionary, and it's showing you the ones that are closest to what you've typed. You follow? And that's what we'll make. We'll make a spell checker. Alrighty. I think we'll leave it at that for today then. That's the edit distance algorithm. That's your lab distance.